We talked a little bit yesterday by filling in the notes on this page about systems of equations. Okay, if there's 3 equations with 3 variables, it is a 3 by 3 system because it has 3 equations and 3 variables. Okay, if it's like this, it's a 2 by 2 system because it has 2 variables and 2 equations. Okay, now you guys have seen these points before, right? We've always called them ordered pairs. It even says which ordered pair shows the solution to the system. So if I had had you do this problem, you would have found that the answer was B, because B works in each one of them. For it to be a solution, it has to work in both equations, yes? Okay. Have you ever seen a point like this before? With 3 things in it? Okay. That's called an ordered triple. Does that make sense? An ordered pair has 2 terms and an ordered triple has 3 terms. That also means it has 3 dimensions. Can you think how that looks in your head? So it has an x-axis and a y-axis and a z-axis. Comes this way. Okay? Don't try to grab it. It's not there. Okay? So, back here, we'll talk about that later on, okay? But I'm just making sure you understand, because we skipped this part of the worksheet yesterday because of time, so I'm going to go back and cover that and make sure you understand. When we have 3 variables, especially x, y, and z are the traditional variables that we use, okay? Unless we're using like meaningful variables in a word problem, it's typically x, y, and z. 3 dimensions, x-axis, y-axis, z-axis, and it comes straight out from the paper, okay? When we write it, how do we know which one of these is x, which one is y, and which one is z? Alphabetical, right? Alphabetical, okay? So x, y, and z, that would be the solution, okay? So on your homework last night, hopefully your homework looks like this. Because it did say shade in. Were you supposed to shade in the ones that were correct or the ones that were not correct? And how did you figure that out? You read the directions. Yay! I'm so proud of you. Okay, so if you did the part at the bottom, remember it's always the math that I'm always going to be concerned about. And if there's a puzzle or something like that, that's going to be like way further down the list. Not even secondary, it's way further down the list. But if you did, it said, if they give you ruled paper, write the other way. So that's a pretty rebellious statement, yes? What? Did you get something wrong? Your okay. Your ruled paper, okay. You can try better next time, yes? Okay. Okay. So, this is the other paper I gave you yesterday, Graphing 2 by 2 Systems. Okay? We're not going to do a lot on this because when we did graphing before, first of all, we had to stop and go back because our graphing skills were not the best, but now they are the best. Okay? So, our graphing skills are great, so we don't have to do a lot of extra practice on our graphing skills. Okay? I do want to make sure to get some of these blanks filled in here at the top. Okay? Do we need to take the time to fill in the tables and plot this? What's important for you guys to know about when we graph a system of equations? Which ordered pair appears in both tables? Well, we don't know exactly, but how about if I tell you it's 2, -1? Okay? What do we call this point in terms of the system? If it appears in both tables, what's it called? The solution to the system. What do we call this point in terms of the graph? The point of intersection. Okay? We did talk a little bit about that yesterday. I just want to make sure we have it written down, okay? So when the equations in the system can be graphed, then the blank to the system can be described using the blank of the blank of blank. Yeah. The solution. Good. The solution to the system can be described using the close. We're going to say coordinate of the points of intersection. Very good. Then it says why. Do you know why? Tell me. Okay. Anybody else? It's the point that's shared by both equations. Very, very good. Okay? Very good. So, number 1. Use the slope and intercept of each linear equation to generate the graphs. Okay? So if I'm graphing this, I'm going to go, what do? Start at 2 where? Up 2. So it's a y-intercept. Rise 3, run 2. Rise 3, run 2. Can I fall 3? If I run backwards 2, right? So there's that line. How do I graph the other line? Rise 3, run 1. Rise 3, run 1. Or fall 3, run backwards 1. So there's that line. So where is my solution? 2, 5, and why is that my solution? It's where the 2 lines intersect. It's the point of intersection. Now, do you see why we're not going to do a lot of these? Because why? They're real easy, okay? I would rather use your time in other ways, okay? So on the second page here, I would like you to circle number 3 and number 5. This says, oh look, if you have these 2 equations, you got to get them in slope-intercept form, and then use your calculator to graph them, and then look at the table in your calculator, and then find the solution. Really? Can you do this? We're going to do, well, first of all, they give you an example of 1, so I would like you to do number 7. I mean, if that's not enough, I can give you more. Oh, you're good? Okay, good. Okay, so this page, this last page, there are sometimes things are not what we expect. Okay? What type of lines are these? Parallel. This kind of system is called an inconsistent system. Any ideas why it's called an inconsistent system? Because they never meet. If they never meet, how many solutions do they have? 0 solutions. Sometimes the empty set is used to describe the solution to such a system. Do you know what the empty set symbol looks like? Nope, it looks like this. Okay? What kind of lines are these? The lines intersect. Very good. What type of system is it? Consistent. Very good. So you guys already knew that? Oh, you used your context clues, didn't you? Wait, even in math you can use context clues? No way. How many solutions are there? One solution? Did you just say our English teachers taught us good? Wow. Okay. What is this represented by? One solution, which is represented by the point of intersection. If the two equations in the system graph into lines which intersect at a single point, they are called Yeah, because in math, apparently, when we find words we like, we use them over and over again for different things. I don't know why. Maybe we figured out how to spell them and we don't want to have to learn how to spell anything else. Okay? These are called independent lines. They don't depend on each other really for the value of the solution. It's just that one place where they cross. Okay? So what kind of lines are these? The lines... We could write are the same, but we're gonna put another word that you're gonna have trouble spelling. They coincide. So what kind of lines are these? What kind of system are they? It is consistent. And I guess you can put very consistent if you want. And blank of solutions. Okay, first of all, you know if it says and, this word is going to start with a vowel, right? It doesn't necessarily have to be an A, but it's a vowel, okay? No. Infinite. An infinite number of solutions. Or, what? Every point on the line. If the two equations in the system have the same graph, then they are called dependent equations. Okay? $11, $14, $15. Guess what I gave you? Guess what I gave you? One of each. I gave you one of each. Okay? Okay. Any questions on graphing 2x2 systems? Okay, go to this one. I gave you this, yes? Okay. When you solve systems by algebraic methods, there is more than one way. Okay? I'm going to teach you at least two to start with. And some people are like, just teach us one, we'll learn it and do it. Well, that's all fine and good, but there are certain situations that one way is better to use than the other way. One way is faster to use than the other way. Okay? There's also the idea that some of you learn one way better than the other one, and you might have like a favorite. Don't you have like a favorite formula? I know, we're all math nerds, we do. Okay? But there's like today especially, I'm going to teach you two different ways to solve a system algebraically. Okay? I like one way better than other ways, except in certain situations. Okay? In certain situations, one way is faster. And so one of the things I'm going to do is, first of all, teach you both ways, how to do both ways. But second and most importantly, I want us to be able to figure out which way is best on any particular problem. Fair enough? So we're not just learning how to do it, we're learning when to do which way. Fair enough? Okay? What's our objective today? Today I will solve systems of equations in a variety of different ways. How many ways have we already learned? One, graphing, right? We've already learned graphing, so hopefully we'll learn at least one way before you leave. Okay, looking at the time now, it looks like we're going to get one way in before you leave. Okay, so we'll get the other one on Monday. All right. So the first way that we're going to learn is called substitution. Substitution can be used to solve systems of equations algebraically. So let's say this is our system. Okay, this is our system. So what we do in substitution is we solve for one variable. It doesn't matter which variable, but we're going to choose one and solve it. We have four choices. We have this one, this one, this one, and this one, right? Two equations in each, two variables in each equation, and we have two equations, so we have four possibilities. So we have to choose a variable to solve for. Now, you guys are pretty like outdoorsy, right? How many of you have animals? How many of you have like dogs? So has your dog ever had babies before? If it's a girl, obviously. Okay. The rest of you, can you imagine what I'm talking about? Okay. So every time the dog has babies, there's usually a runt of the litter, isn't there? And what does that mean? It's the smallest, right? Okay. That's what we're looking for here. We're looking for the runt variable. No, that's not correct mathematic vocabulary. But you know what I'm talking about when I say a runt. Okay, so let's use some prior knowledge that we know and use it in math. Let's look for the runt variable. What do I mean by that? The smallest number? Well, 4 is pretty small. I have a 1 and a negative 1. Which one would be considered the runt variable between 1 and negative 1? It would just be the x, because it's just 1. I don't want to have to deal with the negative if I have a choice. Okay, so this particular variable is my runt variable. Do you see what I mean by runt now? It's the smallest one. There's no multipliers. There's no negative signs. Sometimes this one might be our runt if all the rest of them have numbers with them or something like that. Okay, but for now we're going to solve for the x. So let's choose to solve for this x. How do I solve for that x? If I add y to both sides, I get x equals y minus 11. I don't want to. I could if I wanted to, but I don't. Okay. Now what I want to do you know what x equals? Yeah, I know x equals y minus 11. I know exactly what x equals. I'm going to go to the other equation. I'm going to start rewriting the other equation. But I'm not going to write x. Whenever I get to where x was, I'm going to write what I know x equals. It always makes me happy when you say, oh, I remember this. Distribute to both terms. So I get 7y minus 77 plus 4y equals negative 22. Now we're just solving equations. Do you see why we couldn't go on from solving equations until we understood it? Because guess what we're doing now? Solving equations. Okay? On the left-hand side, what do we end up with? 11y minus 77 equals negative 22. Add 77 to both sides. 11y equals 55. Can we do that in our head? Okay. Y equals 5. Yay, that's the answer. Why not? Why is that not the answer? I got to find x. Oh, okay. So if I take y and go back up here, x is going to equal 5 minus 11, so x equals negative 6. Yay, that's the answer. Why is it not the answer? Because the solution to a system of equations is where they cross. Even when we solve by substitution, we write our answer as a point. Negative 6, 5. Yay, that's our answer. For real. Yay, that's our answer. Okay? That really is our answer. Okay? You get the idea? Yes or no? Okay. Let me check something out real quick. Let's see. Kennedy, choose a number between 1 and 4. Okay, you're going to do number 3. Does anybody else want to choose a number between 1 and 4? You guys crack me up, by the way. Okay? I also need you to do number 9. That's all. Okay? I need you to do number 9. Just 3 and 9 on this packet. Okay? We have another couple minutes, so let's fill in this on this page real quick. Okay? If I subtract 5x from both sides, I get y equals 2 minus 5x. When I substitute that on over here, I get 10x plus 2 times 2 minus 5x equals 9. When I distribute, I get 10x plus 4 minus 10x equals 9. 10x minus 10x? 0. That's 0, so 4 equals 9. 4 doesn't equal 9? Ever? So did I do something wrong? It just doesn't work. Okay? So if you get something like 4 equals 9, if you end up with an equation that is not true, or let's even make it more mathematical, okay, never true. 4 will never equal 9. The system has no solutions. Or it is, remember from the other worksheet? It's inconsistent, so graphically the equations would be parallel. P-A-R-A-L-L-E-L. So what do you think is going to happen if I did this one? Same thing? Can I do it fast enough? If I add 6y to both sides, I get x equals 6y plus 16, or excuse me, 2x, so x equals 3y plus 8. So if I substitute that in over here for x, negative 3 times 3y plus 8 plus 9y equals negative 24. Remember, guys, this is on the video. You can go back and watch it and get the notes if you need to, okay? Negative 9y minus 24 plus 9y equals negative 24. Negative 9y and positive 9y? 0. So negative 24 equals negative 24. Not only is it true, it is always true. The system has what? Infinite solutions. Or it is consistent and dependent. Okay? Or graphically the equations lines would be the same. Or that other word that we put, coincide. Right? Okay? Any questions about this? You got it? So you have these two, you have 9 and 3. And then on this other packet you had 3 and 5 and 7. And these 3 down here. Okay? Guys, I am assuming that you're going to do this in your calculator, so will you have a graph written on your paper? No. You'll have what type of lines they are, what type of system, the type of solution, and the solution if it exists. That's all. Okay? And you can get all that by looking at the graph from your calculator. All right? Any questions?